Okay, guys, let's continue. So we were talking about the LU factorization of a matrix. So we are going to consider another case here where actually, what is it, row interchanges are necessary during Gaussian elimination. And after that, I will finish the class for today. Maybe if I have time, I will solve some problems and share with you. And tomorrow we will talk about 3.5 subspaces, basis, dimension, and rank. And the 3.6 is left, and we will have actually talk about 3.6 next Monday. About next week, I'm thinking actually to have class on Monday and Tuesday, and maybe one day you'll have practice, and you'll have midterm maybe Wednesday or Thursday. Okay. So not Monday and Tuesday, because Monday and Tuesday also you have to practice some questions from 3.6. But after that, I'll give you maybe 1 or 2 more days and you'll have midterm. And all midterm questions are from chapter 1 to 3, not including 3.7 applications. Okay? Good. So, okay. Number 10. All right. Now, the theorem says that if A is an invertible matrix that has an LU factorization, then L and U are unique, right? If A is an invertible matrix that A has an LU factorization, then L and U are unique. So actually, when you just talk about LU factorization, you have to keep in mind this definition. We are talking about a square matrix, right? Let A be a square matrix, then a factorization of A as LU, where L is unit lower triangular and U is upper triangular, is called LU factorization of A. So A is a square matrix. So it says that if A is invertible matrix, then it has an LU factorization, then L and U are unique. Okay, so 2 things are given here, 2 conditions. Number 1 is A is invertible. Second one is it has LU factorization. Now here we have to show that this L and U are unique. So uniqueness in math, how we prove that actually it is unique? We just suppose that it's not unique. Actually, we have 2 possible LU factorizations. That is mathematical tradition that is used to prove things. Okay, let me just use this color. Suppose A can be factorized in 2 different ways. That's L1, U1. And second one is, let's say, A also in different way. I can find LU factorization of this one. Okay, and we know that this L1 and L2, these are unit lower triangular matrices, and U1 and U2 upper triangular matrices. Okay, so since A has inverse, right, that means that also this L and U, they have inverses. So that means that from here A equals this, A equals this. This implies that L1 U1 must be equal to LU U2. Okay. So now from here, let me just multiply, let's say, both sides from the left by, let's say, let's start from the right. So L1 U1, let me multiply both sides by the inverse of U1. So also here we have L2, U2, here we have U1 inverse. And what is U1 inverse? That's equal to I, and that thing is equal to I. So here we have L1 equals L2, U2, U1 inverse. Now, let me just multiply both sides by the inverse of L2 on the left. So what do we have here then? Here we have L2 inverse, L1. Here we have L2 inverse, L2, and here we have U2, U1 inverse. So these 2 things, right? L2 inverse and L2, that's equal to just I. So I times any matrix, that's just equal to that matrix. On the left, what we have here? Here we have L2 inverse, and here we have L1. On the right, U2 and U2 inverse. Okay, so we know that the product of lower triangular matrices also is lower triangular matrix. That means that if you're given, let's say, L1 and L2, if you multiply this matrix together, again, we have lower triangular matrix. Or if you multiply upper triangular matrix by another upper triangular matrix, again, we get upper triangular matrix. Actually, it is given as an exercise. You have to prove it, okay, when you're practicing those questions. So on the left, and also actually the inverse of lower triangular matrix, again, it is lower triangular matrix. And inverse of upper triangular matrix, again, also it is an upper triangular matrix. So just accepting this as a fact, actually on the left, we have lower triangular matrix. And on the right, we have upper triangular matrix because this one is lower, unit lower triangular matrix, unit lower triangular matrix. This one is upper triangular matrix, upper triangular matrix. So the product using this fact, it is lower triangular matrix. On the right, we have upper triangular matrix. And actually, we know that this lower triangular matrix means all the entries in the main diagonal, they are 1, 1, 1, right? Below this and upper this is equal to 0. How about this U? Actually, below the main diagonal, all the entries are 0. When actually this lower triangular is equal to upper triangular. If these matrices, they are equal if and only if actually this L equals U, and that's equal to identity matrix. Identity matrix means here in the main diagonal, let's say if you're talking about 3 by 3, 1, 0, 0, 0, 1, 0, 0, 0, 1, right? All these diagonals must be equal to each other, right? That is the only case. That means that here, that thing actually, what is it? This L and U, that's equal to I, right? Okay. All right, here not. Okay. So that means that from here, that thing, right, is equal to I. From here, that thing is equal to I. So if you just show the first side, for example, let's say this one. So here we have L2 inverse times L1. Okay. Here we have L1. That's equal to I. Now, if I multiply both sides by the L2, what we have here, L1 is equal to L2. In a similar way, from here, also we can show that actually multiply both sides by U1, and you will have that U1 is equal to U2. So that means that actually our assumption is wrong. Actually, these two things, they cannot be different. Even if it is so, they must be equal to each other because U1 must be equal to U2. UL1 equals UL2. What does it mean? It means that this LU factorization is unique. Okay. All right. I need to change order. So we now explore the problem of adapting the LU factorization to handle cases where row interchanges are necessary during Gaussian elimination. Because as you remember, actually when you are exploring or finding the LU factorization of a matrix A, actually we did not use any row interchange operation there, right? Then actually we could write A as a product of L and U. Now here, if you consider this case, what happens actually when we are using or applying elementary row operations? For example, if you are forced to use row interchange, what we have to do, how do we handle this situation or this problem? So now we'll talk about this thing. Actually, we will call this PTLU factorization. Assume that actually I have to reduce this. I mean, we need to write this A as the product of L and U. That is, let's say we are trying to find the LU factorization of A. So the first thing we have to do here is, okay, the first step here is R2 minus 3R1. So here we have 1, 2. Yeah, let me not use reds. I don't like reds. Maybe purple. 1. All right, my glasses. Okay, here we have 1, 2, negative 1, right? Multiplies by negative 3, and at here we have 0, and here we have 0, and here we have 3 plus 2, here we have 5, right? And as you see here, if I just add the second one, R3 plus R1, here we have 0, here we have 3, and here we have, what is it? 3. Now, here we have this pivots, right? The pivot element here, it is 0. Multiplying the second row by any number, and if we add this to the third row, we cannot create a 0 here, right? So what should I do here? Actually, I need to interchange this, but if I just inserted this A, let me just write A star or something like this. How about if I do this thing? Here we have 1, 2, negative 1. I write the second row here, so I will have here negative 1, 6, 2, and here we have negative 1, 1, 4, right? So in this case, the first one is, okay, what is this? R2 plus R1. And also, no, why did I write like this? Here we have minus 1, 1, 4. I should write it here. Okay. Okay, yeah, I'm just interchanging the first and second rows. Minus 1, 1, 4, minus 1, 1, 4. Third row is 3, 6, 2. So this one will be 3, 6, 2. Right? So R2 plus R1. So here we will have 1, 2, minus 1. Here we have 0. Here we have 3. Here we have 3. And now multiply R3 minus R1. Multiply the first row by negative 3 and add it to the third row. Here we have 0, minus 6 plus 6. Here we have 0. And here we have, what is it? 3 plus 2. Here we have 5. Okay. Now what we have here, just 0. That means that entry is equal to 0, because to get 0 here, I should just multiply this thing by 0 and add to this row, right? And now, actually, how can I convert this A into this A star? What we did here is just we interchange second and third row, right? So if I multiply this A by E1, let's just say define this E1, that's element row operation. I mean, the matrix that is 1, 0, 0. Here we have 0, 0, 1, and here we have 0, 1, 0. Actually, what is the effect of this elementary matrix on A? And see here, how did I obtain this? By interchanging the second and third row of an identity matrix. So if I just multiply this E1 by A, what is E1 by A? That gives us this matrix, that gives us this A star, right? Which is equal to that thing, right? And this is equal to U already. And how about L? So here we have L. L is 1, 0, 0, 1, 0, and here we have 1. What is 2, 1 entry here? Here negative 1, right? And how about 3, 1? Here we have it is 3, and that thing is 0 because we didn't have anything. And how about U? U is that matrix 1, 2, negative 1, 0, 3, 3, 0, 0, 5. Right? So now this one is L, this one is U. What we have here is E1 times A. That's equal to LU, right? And what is this L1? Just I use this one, right, to interchange the rows of matrix A, so that without any row interchange, I can reduce this A into reduced row echelon form of A, right? Anyway, this is how we handle the situation. As you see here now, I can write this A as, what is it? E1 inverse. If you just multiply on the left by the inverse of E1, and here we have LU. Okay, so we'll just give a special name. That thing is PT, because what is actually E1 inverse? It just, what is it? Permutation of the identity matrix. Okay. First, let's start with this definition: permutation of a set of objects. A permutation of a set of distinct objects is an arrangement of the objects in a specific order without repetition, right? For example, a simple example, let's say here we have three numbers. Okay, here we have A and B and C. Okay, and if you're using this A, B, C, this is a kind of this car plate. In how many different ways I can write here? Either I can write here A, B, C, or A, C, B, or B, A, C, or B, C, A, or C, A, B, or C, B, A. Here we have 6 different ways, right? So the permutation of these actually letters, right, is 6 here, because here we have 6 different ways in 6 different orders or specific order. I can put them or place them into these rectangles. So that's just when we say permutation of set of distinct objects, we mean that's just arrangement of the objects in a specific order without repetition. Okay. And how about permutation matrix? Permutation matrix is a matrix obtained by permuting the rows of an m by n, what is m by n square matrix, right? Identity matrix according to some permutation of the numbers 1 to n. So 1 to n means actually the row interchange how many times you are doing, maybe 2 times or maybe 3 times or 4 times. So every row and column therefore contains precisely a single one with zeros everywhere, because we are just interchanging, right, the rows of identity matrix. That means that we know that in identity matrix, every row or every column, it has a single one, and the rest of the entries in that particular row or column, they are zeros. So for example, let's say that is also one for permutation, right? That's permutation matrix. How did I obtain this? We just permuted, we just interchange the first and second row. And how about here? I interchange first, actually this one, it must be at the top, this one, it must be at the bottom, and this one, it must be in the, what is it, in the middle. So actually we just use 3 different operations here. In a similar way, there's also another permutation matrix. As you see here, each column or each row, they contain exactly only one. And how did they obtain this? By interchanging the rows of an M by identity matrix. Okay, it's also like something like elementary, actually it's also elementary math, but it's a special one. So consider 1, 2, -1, 3, 6, 2, -1, 1, 4. We have already done in the previous example. So I'm going to skip this. So here we have a theorem, because now the question is, how can we find actually that P? Because in this example, what is it? Okay. If we just, all right. So if P is a permutation matrix, then P inverse is equal to PT. Okay, why do we need this theorem before we continue this? If you're given A, assume that during actually while we are in the process of reducing this into reduced row echelon form, if we are forced to make some row interchange, maybe how many times? Maybe 1 times, 2 times, 3 times, let's say this K times. So that is, let's say here we have EK minus 1 dot dot, here we have E2, E1. Let me just write only E sub K. Okay. And here we have A. Then actually I can just write this one as LU, right? Now from here, we know that this A, actually this one is, what are these? These are actually elementary matrices. They're just obtained by interchanging the rows, right? So actually each one is permutation matrix. So if I just write this one as P, let's say this one is P sub K dot dot dot, P2, P1, and here we have A. So that's equal to LU. Now, let me just multiply, denote their product as P. That's just single permutation matrix. And here we have PA is equal to LU. Now, how can I find this A? If you multiply both sides by the inverse of P on the left, then we will have here A equals P inverse LU. Okay. So now there's a question. Okay, we know this. Okay, actually that's equal to P inverse LU. The question is, how do we compute or find the inverse of P inverse? Actually, that theorem, the next theorem, talks about this. Actually, the theorem saying that, okay, it says it's very easy. Even we don't have to compute anything. Just P inverse is equal to transpose of that P. And we know how to find transpose, right? It's just equal to PT. And why is it so? To show this one, actually, since P inverse equals PT, that means that we have to show that this P transpose times P, it should be, it's equal to I. We have to show this time, right? But the ith row of PT is the same as the ith column of P, because this transpose means, right? That means that's, what is it? Row I of PT is the same as column, right? Column I of P by the definition, because it's transpose as a P, right? And these are both equal to the same standard unit vector E, because P is a permutation matrix, right? That means that, for example, here, if you just write this row I of PT, right? So that means that if, let's say, J's entry is equal to 1, and also this one, actually J's entry is equal to 1, because we are talking about something like this, let's say, if you're talking about 4 by 4 matrix, let's say row I of PT is something like this, 0, 0, 1, 0. And the ith column of P, it should be something like this, 0, 0, 1, 0. And the third entry is 1. Also, this one is third entry is equal to 1, right? It means this. Okay. So from here, then actually this P transpose P. Let's talk about this one. What is I entry? Because I have to show that that's equal to 1 and other entries are equal to 0. What is it? It is just ith row of PT, right? It is ith row of PT, right? PT, right? And times i's column, it's the i's column of P, right? This is how we evaluate the product of two matrices. This one is, we need to multiply i's row of PT by i's column of P, right? Since actually, as you see here from here, that is the one, actually they are placed in the same order, right? So that thing is equal to, just equal to, this one is unit vector, this also unit vector of the same type. So here we have E transpose, and here we have E. This one is E transpose because one is row vector, one is column vector, and which is equal to E dot E. If you remember how to convert this matrix product into dot product, and which is equal to 1, because 0 times 0 is equal to 0, right? 0 times 0, 1 times 1, and 0 times 0, right? This shows that diagonal entries of P transpose P are all 1s, right? Because this one I means these are all diagonal entries, 1, 1, 2, 2, 3, 3, 4, 4. Now we have to show that all other actually entries, they are equal to 0. How do you show that? How about here? P, T, and P, and I, J entry, when I is not equal to, I is not equal to J. So here we have again, that one is ith row of PT times J's column of P, right? Which is equal to E transpose, and this one is EJ, let's say that is E prime, but they're different. So which is equal to E dot E prime, that's equal to 0. Why? Because here, the one in this vector and one in this vector, the order is not the same. right? Because here I and J, they are different. Now from here it shows that actually all entries above the main diagonal, below the main diagonal, they are equal to 0, and all entries in the main diagonal, they are 1s. And that means that since actually, so the product of P transpose P is equal to I, and since P transpose P is equal to I, this shows that, right, that thing, actually, it should be, it must be the inverse of P. So that P inverse must be equal to P transpose. And to find the inverse of permutation matrix, just we need to, what is it, transpose it. That's how we obtain this. Okay, definition, another definition here. Let A be a square matrix, a factorization of A as P, T, LU, where P is a permutation matrix, L is unit lower triangular, and U is upper triangular, is called a P, T, LU factorization of A. So actually now we attach a special name to this factorization, that is P, T, LU factorization. Okay, another example. What is it? It says find PTLU factorization of this matrix. Okay, let's just do this. And do we have any? Okay. Oh, we have 3 slides, and after they will finish the class. Okay. All right, 0, 0, 8, 2, 3, 5, 4, 8, 9. Right. So as you see here at the top, we have 0, 0, 0. So somehow it should be actually at the bottom, right? So first, how many permutations I should make here? 2, right? Because I need to interchange the first row with the second row and the second row with the third row, right? So if I do so, what do we have here? So here we have this P1 will be, actually I need to change the first row with the second row. So here we'll have 0, 1, 0, 1, 0, 0, 0, 0, 1, right? And I should multiply the result by one more time by P2. So P2 is change the second row with the third row. So that is 1, 0, 0. The second row of identity matrix is, what is it? 0, 1, 0. Third row is here, 0, 0, 1. Right? At the time, if we do so, here we'll have P1, P2A. What we have here? Here we'll have this thing. 2, 3, 5, 4, 8, 4, 8, 9, 4, 8, 9, and this will be at the bottom, 0, 0, 8. Okay. So we know that actually that thing is equal to just P. Later I will use this. Now let's continue here. So the first one is, what is it? R2 minus 2, R1. Right? It is 2, 3, 5. Multiplied by negative 10, and here it is 0. Negative 6 plus 8, it is 2. Negative 10 plus 9, it is negative 1. And here I don't have to do anything. It is just 0, 0, 8 already. So now it is ready. Good. Now also let's find this P. What is P? P equals, okay guys, we know that first it should be like this. P1 first, then P2. So that is P2, P1, right? And here we have 0, 1, 0, 1, 0, 0, and the 0, 0, 1, right? And multiplying this by P1. What is it? 1, 0, 0, 0, 0, 1, 0, 1, 0. Actually, what is the effect of this P2 on P1? P2 is just interchanging the second and third rows, right? So this P2 will just interchange the second and third row. So this will be equal to 1, 0, 0. So 0, 1, 0, 0, 1, 0. And here we have, okay, no, P2, why did I? Okay, first here we have P2. 1, 0, 0, 0, 0, 1, 0, 1, 0. And here we have P1. 0, 1, 0, 1, 0, 0, 0, 0, 1. Okay, so this P2 is effect on P1. It's just we need to interchange the second row with the third row. So that's the second row and the first row and third row. So here we will have 0, 1, 0, and this will be 0, 0, 1, and this will be 1, 0, 0. If you multiply, you get the same thing, right? Now immediately, how about P transpose? P transpose 0, 0, 1. So the first column will be the first row, 0, 0, 1. Second row, 1, 0, 0. Third row, 0, 1, 0. Right, that's PT. So now that this A is equal to PT LU, which is equal to PT is the thing 0, 0, 1, 1, 0, 0, 0, 1, 0. And here we have L. This one is U, right? What is L? Only this 2, 1 equals 2. So that is 1, 0, 0, 1, 0. Here we have 1. And 2, 1 is 2. Here we have 2. And others just 0, 0. And how about U? U equals this thing, right? So that is 2, 3, 5, 0, 2, negative 1, 0, 0, 8. So that is PTLE factorization of matrix A. Okay, find PTLE factorization of the following matrices. Okay, these are from exercise. I will leave this, you will leave with your assistant teacher. And here I will finish the class with this theorem. And it says that every square matrix has a PTLU factorization. Okay, it is not UL, should be LU. Okay. Every square matrix has a PTLU factorization, right? And we know that when we are reducing a square matrix into U, for example, if row interchange is not necessary, right? And if it is invertible, always it has LU factorization. But here, now, even if we have to do row interchange, just applying this PT, right? We can just change this into that good form so that we don't have to do any row interchange. And after that, we can, what is it, find the PTLE factorization of a square matrix. People throw stone at you, don't throw them back. Collect them all and build an empire. Guys, that much is enough for today. Thank you very much. Maybe if I have time, those examples I will just solve and share with you. You will see. Otherwise, you will do them with the team. See you tomorrow. Tomorrow we'll talk about subspaces, bases, dimension, and rank. Thank you very much. See you tomorrow. Bye-bye.